Hello and welcome to another edition of Monday Night Calculus. I'm your host, Curtis Brown. I'm here with Steve Kokoska and Tom Dick. I'm super excited to have these guys here with us tonight. We will be chatting a little bit about implicit differentiation. Really excited about that topic. And I did see a couple of questions already come in, Steve. So we've got a few things to get started. Really excited for that. But before we get started, I want to just remind you guys that the bulletin board post, the link to that has been posted in the chat there, and that's where you can find all of the previous recordings. You can find links to those previous recordings as well as the problem sets for those previous recordings and for tonight's session. So if you're interested in following along or downloading the PDF so you can see what Steve is working on and some of the things that Tom's going to talk about, it'll all be there ready for you to go. So Steve, I know you've got some stuff lined out for us. Here we go.
Okay, thank you very much, Curtis. How's the screen? Okay.
Looks great.
Okay, I'm going to bring this a little closer so I can write on there. And I'm going to try to make this a little bit bigger here just to make it a little bit easier to see. How's that? Okay.
I think that looks great.
Fantastic. Okay. Well, tonight's topic is implicit differentiation. Curtis, thank you once again for arranging all of this. Allison does a great job. And Tom, it's always a joy to work with you. Mark Corrali has sent us a couple of problems as usual. Thanks to him. We want to encourage participants to ask and answer questions and send us any questions you have any, if you have any.
For sure.
And we want to encourage students to participate too. So any of the teachers on tonight, if you want to encourage your students to listen in and ask and answer questions, that'd be wonderful. And in the spirit of Tony Kornheiser, welcome to all our Canadian teachers and students. How about that? Okay.
Welcome. Yes, that's great. We also have some folks in from Tennessee. I saw Tammy Jones pointed out my Northern Lights in the background. So it's great to have Tammy on there too.
Okay. So a little bit of background here to get started before we get to implicit differentiation. Most of the functions that we deal with in AP Calculus, in most of them, the variable y is expressed explicitly as a function of x. So here's some common sort of functions that we might see. Here's a polynomial. Here's an interesting one, x squared times the log of x. You might think a little bit about what the domain is there. And here's another interesting one, e to the x sine x cosine x. Those are kind of common to us. But it turns out that some functions are actually defined implicitly by an equation involving both of the variables x and y. So for example, if we take a look at this one, x squared plus y squared equals 16, or this one, which is one of my favorites, there may be a function or functions embedded or hidden in that expression. Now, in some cases, you can actually solve for y as a function of x. So in this first one, x squared plus y squared equals 16, we recognize that as the expression is the equation of a circle centered at the origin with radius 4. And we know that we can solve that for y in terms of x, and we get two separate square roots, two separate functions. So that here's the circle on the left-hand side, but there's really graphically embedded in there two separate functions. We know that this is not the graph of a function. It doesn't pass the vertical line test. But embedded in there are two functions. One we could write this way, and one the negative square root. So the other one, and I'm going to come back to this here, is one of my favorites, the folium of Descartes. And there's some neat technology in here. We could spend a whole night on this. Maybe someday we will, Curtis.
I think that'd be great.
This is one of my favorite functions here. There's so many cool calculus questions going on. We won't get to these. We won't do any of these tonight. But you might think about finding any places on that curve where the tangent line is horizontal or the tangent line is vertical. And if you look really closely, there might even be a slant or an oblique asymptote in that graph. And a good question is, can you find it? Now, as I look at this function, at that expression, and I think about, well, is there a function embedded in there? I don't think I could actually turn around and solve that for y in terms of x. But just to show you here some of the power of the TI-Nspire, it can actually do this. Now, you don't see all of the output here, but there are actually three separate expressions for y in terms of x. And that is unbelievably cool that the Nspire does that. And here they are graphically. If you think about what that folium of Descartes looked like, one part of that graph is right here. There's a function that passes the vertical line test. There's another one down here. This goes on, okay, forever and ever. And then there's another one over here, just a little bit of arc, another piece there. So, okay, if f is a function defined implicitly by one of these expressions or by this one in particular, then this equation must be true for all values of x in the domain of f. Now, this is really a cool technique. When I think about this or when I teach this, I often am amazed sometimes that this really works, especially when we're finding an actual numerical derivative. So implicit differentiation, we don't need to solve for y in terms of x in order to find the derivative of y. We can use this method to find f prime. And basically, all it says is we differentiate both sides of the equation with respect to x, and we simply solve for y prime. Now, Tom knows that I'm very big on step procedures here. I like these for my students. So here's a procedure for implicit differentiation. We think about y as a function of x. So we have to think of y as a function of that independent variable x. And we differentiate implicitly. What does that mean? You differentiate both sides of the equation with respect to x. Now, there is some question about whether or not the equality is maintained, but in fact it does. That's a separate discussion. But remember that since y is a function of x, we need to use the chain rule. That is often, sorry about that, that is often a part of this that is forgotten by students. But we need to use the chain rule here to find the derivative of an expression involving y, and then we'll solve for dy dx. I often get a question about this. Is it okay that my expression for dy dx involves both x and y? That's a little unusual. We're not used to seeing that, but you know what? That's fine. So let's go back to a couple of these, or at least this first one that I talked about.
Hey, Steve, while you're doing that, we did get a couple of questions about explicit differentiation versus implicit differentiation. And we have one comment here. So explicit differentiation is in terms of one variable only. Can you kind of give us a real brief definition there?
I don't know if I've ever heard that phrase, explicit differentiation, but I would think of that as if we have y all alone on one side and we have only x's on the right.
Yeah.
And then we simply take the derivative of the right-hand side with respect to x to find y prime. I guess I would call that explicit differentiation.
Okay.
Okay.
Thank you.
And implicit is what we're going to try now, where we think of y as a function of x. So let's go back to this one where we had the circle. And we want to find dy dx. So I'm going to go through this one in kind of gory detail, but then I'll go quickly through the others. We take the derivative of both sides here with respect to the variable x. The derivative of 16, a constant, is easy. That's 0. This is the derivative of a sum, so that's the sum of the derivatives. The derivative of x squared is just 2x. The derivative of y squared, we think of y as a function of x, so we need to use the chain rule. This is 2 times y to the first power times the derivative of the inner function. I often say in class, look, I don't know what the inner function is, so I have to write some symbol for that. And I'm using dy dx here, the derivative of y with respect to x. I often get a question at this point, well, look, is it okay for students to use y prime instead of dy dx? Look, absolutely, absolutely. So now I turn around and I solve this for dy dx, and in this problem I've got a minus x divided by y, and again notice that that derivative involves both of the variables x and y, and that's okay. So I want to find the tangent line, an equation of the tangent line at the point minus 3 square root of 7. So this is kind of a long notation here, but I want to take that derivative dy dx, I want to plug in an x equal minus 3, a y equal to square root of 7. And I think I get this expression symbolically. And here's an equation of that tangent line. Remember, on the AP exam, unless it says otherwise, you can certainly leave the equation of the tangent line like that. Now, of course, another way to do this particular problem is, okay, I can solve for y in terms of x. I can pick out the correct function here. I think I'm dealing with the top half of the circle, so I take the positive square root. And I can find, okay, we'll use terminology suggested by a participant. We can use explicit differentiation and hopefully get the same answer. To me, it's really cool that with implicit differentiation, this expression for dy dx gives you the derivative in terms of both x and y for every function y that is implicitly defined by that equation. I find that absolutely amazing, and that's really cool. So a little help with technology. On the left-hand side, I'm using the TI-Nspire, and what I did is I drew the circle in there, and I got an equation of the tangent line through the point -3. I think that's pretty close to the square root of 7. That's really cool, so I can picture this. And I think a neat function on the Nspire is it actually has an implicit differentiation function. So I can actually write in this expression, tell the Nspire what the independent variable is, indicate the dependent variable, and there's the derivative, dy dx. That's really cool. And I can go one step further, find the derivative subject to or such that x is -3, y is the square root of 7, and there's the slope of the tangent line at that point, which is really cool.
Hey, Steve, just to be clear, you're working on an Nspire CAS, correct?
I am indeed, yes.
Okay, I want to be very clear that we're working with an Nspire CAS in this demonstration here, and that is a CAS only functionality.
Yeah, and in fact, you'll notice here, Curtis, I think that this one is, this answer is rationalized.
Right.
And I think Tom will have to address this, but I believe on the non-CAS version, I believe if you do something like this, you'll get a decimal approximation there, which is, of course, okay on the AP exam too, although I don't think you're going to see a question like this. All right, let's take a look at one more here because there's some interesting things going on here. Let's try the implicit differentiation. We have to use the product rule, see if we can find dy dx here, running through this one a little bit quickly here. I take the derivative of both sides. The right-hand side is, whoops, that's easy. On the left-hand side, the derivative of x cubed right there. The derivative of this expression, we'll have to recognize that that's a product, so I have to use the product rule. Derivative of this expression, son of a gun, that's another product. I have to use the product rule there. So I've probably written out way too much here, but I think you can see everything using the chain rule on top of the product rule there. And all the way down at the bottom here, here's an expression for dy dx again, in terms of both x and y, and that's very cool. I don't think I could turn around and solve this expression up above here. I don't think I could solve that for y in terms of x. So that's pretty neat. And here it is with a little help from technology. This is implicit differentiation function once again using the TI-Nspire. And I think that's the same answer I got on the previous page. And here's a graph of this expression. I happen to have used Mathematica to do that, but I think there is a way to do this on the Nspire. Tom may get to that. This is really cool. You can certainly see by looking at that graph that it is not the graph of a function. And I'll just add in a little bit more here for our participants to think a little bit about. It doesn't look like, at least to me, it doesn't look like this graph crosses the y-axis. It doesn't look like x equals 0 is in the domain. So you might think a little bit about that. Is x equals 0 in the domain? Is it not in the domain? How can you justify one or the other? That's a good one. And with implicit differentiation, you can even go a little bit further. You can actually find a second derivative. So let's do one real quickly here. Here's x to the 4th plus y squared equals 16. Let's quickly find the first derivative. Here we go, implicit differentiation. That's pretty easy. Here's the chain rule in here. Did I do that right? 2y times the derivative of the inner function y prime. Solve for y prime. Here we go. Now I want the second derivative. So I take the derivative of both sides once again with respect to x. The derivative on the left becomes y double prime. And on the right-hand side, I have to use the quotient rule, remembering once again that y is a function of x. So I think I've done that correctly, and I'm going to take a quick peek here. You'll notice when I simplify a little bit here, I've got a y prime in there. And I've got an expression for y prime up above, so I can substitute that in here. And I put 3 dots in. I've done a lot of simplification, and there's an expression for y double prime. So just thinking ahead, I didn't ask anything about this, but just thinking ahead, you might be able to use that expression to answer a question or two about concavity at a particular value or at a particular point. That's kind of cool. All right, so at this point in the class, generally, once you learn a little bit about implicit differentiation, we can learn how to find the derivatives of inverse trig functions. So I'll take a quick look at one of them. So here's the definition of the arcsine function. You'll remember that we need to restrict the domain here so that the sine function will be 1-to-1, and therefore it has an inverse. And here's how we'll actually derive. I know that's a dirty word, but here's how we'll actually derive the derivative of the inverse sine. So, okay, I'm going to take a look at this expression. I'm going to take a look and take the derivative of both sides with respect to x. On the right-hand side, I get 1. On the left-hand side, the derivative of the sine is the cosine. Derivative of the inner function is y prime. I'll solve for dy dx, 1 divided by the cosine of y. That's not too satisfying. I'd really like to get that back in terms of x. So we'll think a little bit about this. On this domain here, the cosine of y is positive. We know we can write the cosine of y as 1 minus the sine squared of y, but wait a minute. The sine of y is x. So that means the derivative of the inverse sine is 1 divided by the square root of 1 minus x squared. Very cool. So once you do that, you can probably find some other derivatives here of trig functions. And I'm going to leave you with one problem to think about. I'm not going to solve this one. I don't know why, Curtis. I don't know why this is, but there is frequently a question on the multiple choice portion of the exam about the derivative of a general inverse function, f inverse. And here's the formula which most AP students have memorized, but in fact, you can actually derive that now that you know how to use implicit differentiation.
Oh, that's good.
So that's very cool. Any questions that have come up? If not, I'll switch here. I'll transition and take a look at the problems that we assigned for tonight.
Let me just be sure. I don't think I've seen any questions that have popped up yet, so I think you're good. I think you're good, Steve.
Thanks, Curtis. So the first thing we ask is if y is the inverse tangent, let's find a formula for the derivative of this inverse tangent function. And I can approach this in the exact same way I did a minute ago with the inverse sine. So if y is equal to the inverse tangent, tangent of y is equal to x, I'll take the derivative implicitly. So the derivative of the tangent is the secant squared. There's the derivative of the inner function. Derivative of the right-hand side is 1. This one's maybe a little bit easier. 1 divided by the secant squared. We've got a trigonometric identity in here. And we know that the tangent of y is equal to x. Is 1 divided by 1 plus x squared. That's pretty cool. And let's get a little bit of graphical evidence in here, some confirmation in here. So what I did is I graphed both the arctan function and its derivative in the same viewing window. And one common question, I suppose you wouldn't see this on an AP exam, but one common question you might ask your students is, does this derivative, does it really look like the derivative of the arctan function? Can you justify this? Well, let's see. The arctan function, it looks like here, is always increasing, so its derivative is always positive. And as it levels off here and here, the derivative is getting closer and closer to 0 out as x increases without bound, as x decreases without bound. So it looks pretty good. I feel pretty confident that we actually found the correct derivative. So I know you did these problems, but here's what I got for some solutions. We asked you to find dy dx y prime for this expression. This one's a little different in that when we take the left-hand side, derivative of the left-hand side, the derivative of the outer function is cosine, but the inner function is a product. So taking the derivative using the product rule, I think is xy prime plus y. On the right-hand side, the derivative of 1 is 0. The derivative of the cosine minus the sine y, derivative of the inner function. That's the hard part. The rest here is just a little bit of algebra. Collect all the terms with y prime on the left-hand side, do a little bit of factoring. There's my solution. And for part B, again, just a little different here. Get some other functions in here, e to the y cosine of x. Take the derivative on the left-hand side. Well, let's see. I guess we've got to use the product rule once again. E to the y, derivative of the cosine minus the sine. And let's see, the derivative of e to the y is e to the y times the derivative of the inner function. There it is. Derivative of the right-hand side. Okay, same strategy. Get all the terms with y prime to the left-hand side, do a little bit of factoring, and there's what I got as an answer. And I like to confirm or check my results. So I did that with the TI-Nspire using this expression, using this function, implicit differentiation. I think I got the right answers there. This is kind of interesting. If you take a quick peek, Curtis, down on the bottom right-hand side here, the TI-Nspire CAS version at least left the log of E in there rather than writing that as 1. I'm not sure exactly why. Tom might have an answer for that, but that's kind of interesting.
That is interesting. I'll be interested to hear what Tom has to say.
Well, I think, Steve, I wonder if you used the dedicated transcendental number.
Yep.
Just the letter E. If it just thinks that's a constant E.
You're right.
Gotcha.
That's exactly right, Tom. And I see that now that you mentioned that. The actual Euler's that EE
it's bold italic
is bolded in italics. That's
gotcha.
Right. Mm-hmm.
Okay, gotcha. Very good, Tom. Very good. All right, we had another couple in here, couple quick ones. Find the equation of the tangent line to this curve. I want to get to Tom here, but I wanted to point out one kind of, I think, clever trick. If I want to find dy dx here, and this derivative looks awfully complicated when I took the derivative of the left and the right, you know, one thing you can do is right away plug in the value of x and the value of y. I don't actually have to explicitly solve for y prime right away. So I did that, and I think this expression becomes much simpler because I've got an x equals 0 in there and a y equal minus 1/2. And it was much easier for me to find the derivative y prime is equal to minus 1. So there's an equation of the tangent line, and you might recognize this curve. Curtis, do you remember what that's called?
Nope.
Any of our participants remember what that's called? We'll leave that.
You got me there.
We'll leave that for a question. And while they're thinking about that, so this graph you would probably see if you study polar equations, if
yes,
you study polar coordinates. And so a good question is, can you take this expression, can you convert that to polar coordinates? So I'm not going to do that here, but that's a nice problem.
I just got a response, by the way, Steve. One of our participants says cardioid.
Terrific.
I agree with that. Cardioid. Thank you for that.
All right. Real quickly, here's a couple of other answers. We were discussing how you pronounce this, but we think it's the Cherhausen cubic. This is kind of a neat graph too. Find an equation of the tangent line to the graph at this point, the usual. I find y prime using implicit differentiation. Here's an equation of the tangent line. And again, I really like to back things up graphically here. I like to confirm my answers that I found analytically. And I really do enjoy using the TI-Nspire so that I can see that. I can put the point on the curve. I can find the tangent line. And part B, I think, is really interesting here. We're going to leave a couple of open questions here, Curtis. It says, find the points in the graph where the tangent line is horizontal. Well, as I look at the graph, I can kind of see a couple, but how do you approach that? Well, here's the first derivative that I found with implicit differentiation. I want to set that equal to 0, and I want to solve. Well, how do you make a fraction 0? The only way to make a fraction 0 is if the numerator is 0. So I set that equal to 0. I factor completely. That gives me an x equals 0 and an x equal minus 2. But there's a little bit of an issue here. If x is equal to 0, then y is equal to 0. You have to go back and take a quick peek at the general expression for this cubic, for this graph. So that means that y prime is in an indeterminate form of 0 over 0. Now, my claim is that this graph has two tangent lines at the origin. And so an open question is, can you find the slopes of those two tangent lines? I mean, look what's going on here at the origin. You can almost see those two tangent lines in there. But a question is, how the devil do you find the slopes of those two tangent lines? So we'll leave that open. If I take x equal to minus 2 and plug that back into the original expression, I've got these two values. And there's this Cherhausen cubic with the two horizontal tangent lines in the same viewing window. And that's pretty cool. Very neat. All right, if there are no other questions for me, Curtis, I'm going to turn it over to Tom.
I don't think there are any other questions for you, Steve. So yeah, I'm really excited to see the tech side tonight. I know Tom has a lot of things prepared for us. Tom, I do see your microphone muted, so just heads up. Yeah, I think this is going to be good. I'm really excited.
Okay.
All right. Okay, so I'm going to try to share screen here, see if I can pick out the right thing. Looks like I have lots of windows, so all right. I'm going to start out with the Nspire.
Okay. Hey, Tom, I think we have one more question
Sure.
for Steve while you're getting that put up here. Tammy Jones asks, is that what is considered the negative pedal of a parabola?
The negative pedal of a parabola. What was that? The Cherhausen cubic?
Yeah.
Boy, I don't know if I've ever heard that before. Tom, have you?
I've not heard that term. That doesn't mean it's...
Yeah, right.
I've heard the term pedal in reference to polar.
Yeah, right. The pedal, yeah, the polar coordinates for sure. The polar graphs and those cardioids for sure.
Petals of a rose, right?
Mm-hmm. Right. Mm-hmm. Yeah. And so, I thought people showed a lot of heart in identifying the cardioid.
Oh wow.
I'm gonna go.
Oh wow. That's pretty rough. That's pretty rough.
So, well, shall I go ahead here?
Yeah, take off. Take it away, Tom.
So I took a liberty of Steve had been in contact with Mark Crawley, and Mark's been really good about communicating with us and promoting us and feeding us some good questions from his discussion group. And this was a curve I think Mark uses in his teaching sometimes with implicit differentiation. So you see this y cubed plus y squared minus 5y minus x squared equals 4. And you can see that's a relation that's being graphed here on the TI-Nspire. And I just wanted to show how that works on the Nspire. If we, see, I probably should use this handheld view here. Go to the menu, and I'm going to the graph entry edit. There is a relation graph that you can select. And I've got one relation in there already. It's the relation 1. But now I'm looking at relation 2. And so I'm going to graph something that looks very much like this expression or this equation, except I'm going to change to the constant on the right-hand side. Okay? So I'll just type in, let's see, we have y cubed. And then we'll have plus y squared. And minus 5 times y. And then minus x squared. And then in this expression, I actually put in an equal sign. And now I'm going to put in a different constant here. I'm going to put in -4. And we get another curve, and this one is in red. Let me move the label here. So these two expressions or two equations, their only difference is that constant on the right-hand side, okay? So this is a really nice graph, but there are two separate, and notice this, the blue graph is actually in two pieces. That's the one that had the positive constant. You can see it's color-coded. The color of the expression matches up with the color of the graph. Now, let's go back to the menu, and I'm going to choose Analyze Graph. And you'll see there's dy dx is there, but we have these implicitly defined functions. So let me go ahead and select that. It's asking me which graph. I'm going to go to the blue graph. And I can put a point on that graph. And what it's reading out is the actual slope or the value of the derivative of that at that point. Okay, so this is the implicit derivative. And that point is now movable. So we can see the slopes. Let's see, is this really making sense? It looks like we've got a slope of 0 here. Yeah, that looks good. Okay. And I can even actually, I can't snap it over to the red graph, but I can snap it over to the other part of the blue graph. So I've got this live point on the graph that's showing the value of the derivative at that point. So I think that's kind of neat. It's really good, especially for illustrating things.
That is really cool. We've got a comment in here.
Sure.
Several people now talking about slope fields and how their students like to use the slope fields on the Nspire to do this as well.
Yeah, that's kind of before they had an implicit grapher built in. Slope fields was a technique you could use to recover these kinds of graphs, getting these contour plots. Also wanted to, so some people I think overlook this, but under geometry, we've got points and lines. Oops, let me try that again. All right, so I'm going down to geometry, points and lines. I did it again. I'll try one more time here.
I'll do what an instructor told me never to do. Use the numbers, Tom.
Yeah, okay. And you see tangent. And that tangent will recognize that if you're looking at a function graph, it'll give you a tangent line to the graph. Okay, so I can attach a tangent line to that point, and it gives me the equation of the tangent line. And that point is still movable. So it's giving me that live update with both the slope and the equation of the tangent line.
That's really powerful demonstration, Tom. That's awesome. I do have a question that just came in. How would you describe that smaller blue locus, that smaller blue section down below. Is there some sort of a name that you would give that?
I'm not sure. I think, though, when I look at these kinds of graphs, especially where I have this expression where the only difference here is that constant on the right-hand side, this really reminds me, and I know it's not in the AP curriculum, either AB or BC, but as we go into multivariable calculus, we had a function of two variables. So Z equals a function of X and Y. These would be examples of two what would be called level curves.
Yeah.
That you would see in a contour plot.
That's what I was thinking.
So students who've seen contour maps, this blue line, all the points on it are at the same level. Well, it'd be +4. So if we think of these as being at elevation 4, well, here's another ridge at elevation 4. Okay.
Right.
And they're just separated. They don't, they're just in two separate pieces. While here on the
what went to my
red
mind was topographical maps, right?
Exactly. No, it's a really great, and on this red graph, this is at level -4, but this one happens to be all continuous, all in one piece, all connected, all in one piece. Okay. I did want to show some things on the 84 also. People might say, well, implicit differentiation, TI-84 doesn't even have CAS. You only do like numerical derivatives. Can you really do much there? It's surprising how much you can do on the 84. So I'm going to switch over to that. And I'm going to address one of the problems from that Steve had on his sheet here. I'm going to go to y equals here.
Okay, hold on, Tom. You got to switch applications.
Absolutely. Thank you for reminding me, Curtis. That happened to me last time, and I forgot. So let me go back. And let's see.
Yeah, I didn't wait this time. I wanted to make sure that we called that out. Yeah.
So I'm going to do, well, let's see, stop share and then share again.
Yeah, that's fine.
That's probably the
switch switch applications.
Select a different screen here. For there it is. And here we go. Okay. So again, let me rewind here. So I'm going to look at the TI-84 and the y equals menu. What I've done is, this is that, I don't know how you pronounce it, Schuhausen curve. It was y squared equals x cubed plus 3x squared. And so what I've done here is actually taken the square root of both sides. So I've got a y1 is equal to the positive square root of x cubed plus 3x squared. And y2 is the negative of that. So it'd be the negative square root. And what I'm going to do is I'll go ahead and select those two graphs. And now let's take a look, and I'll go ahead and do this in a zoom decimal window. And there we go. Now the two of these together give us that curve that Steve was looking at. But it's an interesting thing to note here. There's really some fascinating stuff happening at the origin. If you look at this holistically as a single curve, you say, okay, it loops around and intersects itself. And as Steve mentioned, he said, well, you can make an argument for there being a couple of different tangent lines at the origin. But I want you to take a close look at this blue graph and this red graph. There's no tangent line at the origin on either one of those.
Right.
The blue graph has this sharp change in direction at the origin. And the red graph, which is its mirror image reflected over the x-axis, it's also got a sharp corner. And so the derivative of either of these two, these were two explicit functions that together, their union make up the graph of the relation, but neither one of these explicit functions has a derivative at 0. And the point I wanted to make here was, well, this was not the only way to define some explicit functions that would piece together to make this graph. So I'm going to show you another choice.
That's really great.
So I'm going to turn off Y1 and Y2.
Hey, Tom.
Yes, go ahead.
We have a question that's probably on your Y3. Can you show us briefly how you got that piecewise definition there?
Sure.
Walk us through the process, maybe.
Absolutely, absolutely. In fact, what I'll do is I'm going to define Y4 from scratch.
Okay, that sounds great.
Illustrate that, okay?
Yeah, that sounds awesome.
Y3, what I've done here is I'm still referring to Y1 and Y2 here, but here what I'm going to let Y3 be the same as Y1, but for only the x's that are less than or equal to 0. And then I'm going to switch over to Y2 for the x's bigger than 0. Now I'm going to go down to Y4, and I took a shortcut here and just defined it as the opposite or the negative of Y3, but let me just clear that out and enter that from scratch.
Yeah, that sounds good.
So if I go to the math menu and scroll down, I eventually see something called piecewise. And it's kind of a tailor-made thing for entering piecewise defined functions. So let me enter that, and it asks me, well, how many pieces do you want in your piecewise defined function? Well, I just have 2, so I'm going to lower that down to 2. I'll press OK. And it sets up a little template for me to enter my piecewise function. And I'll enter a formula in each one of these spots before the semicolon, and then I need to put kind of what part of the domain that will be valid for. So in this case, what I'm going to do is for Y4, I'm going to put in negative of Y1. For the x's that are less than or equal to 0. So I'll go over to the right of the semicolon, get my x. I'll go to the test menu to get my inequality sign.
Now you can go to the conditions there. See that option there on conditions? That'll give you all of those possible scenarios that you might use over there. So just another option there.
Okay, thank you.
Mm-hmm.
And let me get, and for and here I'll put the negative of Y2.
Right. Yep.
And I'll learn something new today. So when you said conditions, Curtis, what did you mean?
So go ahead and go down to the test menu again, the same way you did before.
The test menu? Okay. So here's test menu.
Now there's a third option over there on the top, not logic, but just conditions. Now
all of those I see where it would take care of putting in the X for you also. I see. Thank you. Yeah, no, that would have been a shortcut that so I'll put greater than.
That's really helpful when you have one of those large complex setups that you've got 3 or 4 pieces and you need to have the and in between your statements.
Right.
So, less than 5 and greater, whatever. So that helps you be able to build those out.
Okay. So I actually did take advantage of it this time. So I got the X greater than all in one swoop, greater than 0. And so my claim is this Y3 and this Y4, these will also piece together to give us our graph, but in a different way. So let's take a look at this graph and see what we get. All right. Okay, so now this is giving me the union of these two is the same graph I had before of the relation, but now I've got 2 smooth curves, and each one of those has its own different tangent line at the origin. So as Steve said, this is there's some really interesting stuff happening at 0, 0 on this graph. If we were to do this parametrically, it would depend on what direction we were moving along the graph, which direction the tangent vector or velocity vector would be pointing. So kind of looking ahead, that would be a chance to revisit this curve. Steve mentioned looking at some curves using polar coordinates. This one might be neat to look at parametrically. So you actually see the difference between a intersection point and a collision point. So, all right.
Yes.
Any other questions that might have come up, Curtis?
Yeah, there actually was a question. I think it was related to the how you had Y1 and Y2, and then what that graph actually looked like. Was the question was, what does the table look like? I'm sure that would actually apply really nicely here as well. So,
so we could look at.
Can you show us maybe how the table looks for those two, or maybe even all three different of the functions? Or sorry, the four different ways that you have that defined there.
Oh, okay. So
maybe you can turn on
Y1
and Y2 and check that out as well.
And then take a look at the table.
Yeah, that gives us a little better picture now. We can see. Mm-hmm.
And when you have an expression where y squared is an expression in terms of x, I think our first kind of knee-jerk reaction is, oh, I'm just going to solve and do plus or minus the square root. But one can see here that, you know, if I want to actually have a tangent line at the origin, that might not be the best way to go.
Yeah. Yeah.
So we kind of mixed, or the Y3 and Y4 was mixing and matching the top and bottom halves of that curve in different ways in order to piece it together.
Yeah.
There is a lot of symmetry, though, that you can see from the table, both from the table and the graph. These numbers. Okay. All right.
Very unique, very good, ingenious way to do that, Tom.
Now,
so
I
Tom,
think I made, yes.
Can I ask a quick question?
No.
So you're okay. The heck with
You're
it.
forbidden.
That's a tough crowd.
Go ahead, Steve.
So
you're going to stump me, I know. All right.
No. I'm curious now. Maybe you don't want to do this, but on the 84, for your functions y3 and y4, can you on the 84 on the graph screen or on a home screen, can you find a numerical derivative at 0?
Should be able to for Y3 or Y4. Let's take a look.
Okay.
I'm going to quit. And I'll tell you what, let's look at the graph one more time.
Yeah.
Oh, this is all of them. But the Y3, I think, was
Y3 is the black one.
Black graph.
Try that one just for the heck of it.
What's that?
Try that one just for the heck of it. Yeah.
So let's try Y3. So I'm going to go back to the math menu, and down there at number 8, we see the numerical derivative. And I'll take the derivative with respect to x of Y3. And we're going to do that at x equals 0. Now, just a reminder, what is the TI-84 actually doing here? Well, a numerical derivative, it's actually doing a difference quotient. It's actually a symmetric difference quotient.
Right.
Picking a point on either side of 0.
Right.
And calculating the difference in y values over the difference in x values. Okay, so let's see what we get.
Ooh, how about that?
Yeah.
And that makes pretty good sense.
It does make sense. That number actually looks somewhat familiar.
It should look familiar. Pretty cool, Tom.
Yes.
Cool.
Cool. Now, if you did this on Y1, let me go ahead and do that. Now, remember that Y1 has really a sharp corner in the graph at 0.
So what do we want the answer to be?
Well, this is going to give us an answer because it's doing that symmetric difference quotient, but it's not going to
not going to be one we
trust
like
it at all. And that's where the graph is kind of handy to be, do a reality check. So let me go ahead and put in Y1.
So while you're tackling that, Tom, and talking about the way that this works, I did get a question in that asks if this is able to be done on the TI-Nspire CX CAS. And I think we're talking about, your ability to break it apart and draw the graphs the way that you just
so
did.
the piecewise, for sure.
To show that piecewise. And yes, there's absolutely a way to do the piecewise functions that way for sure. So I don't know if you wanted to share that or if you wanted to had some other examples here.
Well, I think I might stick with the 84 just for now. And
yep.
But this value here is going to be really problematic, Steve, because it's around that sharp corner. But it's still, what it did was pick 2 points really close by. And so this value here, I want to just say right away that that's actually the graph that is underneath these 2 graphs has that sharp corner there. So it's actually coming up with this kind of bogus value. But we should know, we should be careful and realize, oh wait, that's not numerical. It is just a numerical derivative, but it gives us a very nice approximation to the slope of the black graph.
Well, this is a great example to show that you just can't believe everything that you get numerically. You've got to think about things graphically too. And confirm things analytically too.
Right.
So this is a good example.
Yeah. So I did want to point out that you can do implicit derivative numerically on the TI-84.
Okay.
And I'm going to go back to another example Steve had. This one we can kind of hold in our heads because it's pretty simple. It's just that equation of the circle. X squared plus y squared equals 16. And so I'm going to go to the calculator menu here. Let me go ahead and clear it out. And let's see, we had x squared plus y squared equals 16. What I'm going to do is calculate, well, bring everything over to one side of that equation. So that'd be x squared plus y squared minus 16. And I'm going to take the, oops, let's clear that. I'm going to take the negative of the numerical derivative with respect to x of that expression I just described in 2 variables. So that would be x squared plus y squared, I'll get the y off the alpha menu, minus 16. And I believe the point you were looking at, Steve, in your example, it was x equal -3, y equals square root of 7. That
Correct.
was the point on there. So I'm going to evaluate that at the x value, -3. Get that value. And now I'm going to take another numerical derivative. But this time I'm going to take the derivative with respect to y of that same expression. So that'll be x squared plus y squared minus 16. And that's at y equals the square root of 7. I've got these 2 values now, and what I'm going to do is just take the ratio of these 2 values, the first one over the second one. So I'll just go up and divide by this one. And that should be the same as the implicit derivative of y with respect to x. Now, I think you got it in symbolic form, Steve.
Right.
What was your answer?
The answer we had before was 3 divided by the square root of 7.
Okay, let me check that out. I'm going to do 3 divided by the square root of 7 just on the calculator.
Oh,
how do you like that?
Wow.
Yeah.
How do you like that? Hey,
so this is what I would
good.
suggest to people if you're using the 84 and you're doing implicit differentiation. By the way, the implicit differentiation questions you would see on the AP exam are almost always going to be on the non-calculator part of the exam.
True. Yep, that's true.
But this is a nice way for you to do a reality check on your answer. Even if you have a symbolic formula where you're doing the general dy dx implicitly, you can just pick a point on the curve and check it, see if it's giving you the right value, and then check it numerically on the 84, which is, and I remember the first time somebody showed me this, I was very wowed. It's using, in essence, it's using some partial derivatives, but I just view it as a kind of an additional way to extend numerical derivative capabilities of the 84 to implicit.
That's pretty cool. That is a really neat example, Tom. Thanks for sharing that one. That was
Sure.
good.
I think I'll wind it up there, see if we have any other questions we might need to address. I could do a stop share and turn it back over to here.
This is a good question here, Tom, that just came in. So is that essentially an application of the chain rule that you've kind of applied there?
Yeah, I would invite people to think through what they're doing with the implicit differentiation. And one thing you could think about would be to move all terms that have y in them to one side of your relation, all the terms that don't have any y's in them to the other side, and think about what then you're working through. And I think it starts to reveal kind of why this works.
Yeah. Yeah, that's really a good, I really like that. That's a good example. And I think that's helpful. That's really helpful. Well, thank you guys very much. Yeah.
Oh, did want to make a point. Somebody mentioned slope fields, and the way that works is if you take a relationship and find the implicit derivative, and then enter that as your differential equation in the slope field plotter, then the slope field, your original relationship, should fit that slope field.
Yeah. Yeah.
But you also get lots of other curves. So
Sure.
Your one implicit relationship will be one of the level curves that's basically mapped out by the slope field, which is kind of cool.
Yeah, that is a cool way to use that. That's a really cool way to use that. So thank you guys a whole bunch for this evening. This was really, really great. And I want to say thank you to the teachers and students who are watching tonight as well. This was a really great conversation. I enjoyed seeing the chats and the things come up in the questions and that sort of thing. We highly encourage you guys to be using this with students and getting your students involved and asking questions here. We certainly are happy to answer them. I do have one more question. I think we can answer this one from the chat directly. So I think we're good there. So just so enjoyed you guys this evening, and I'm really looking forward to our topic for next time. So I guess we'll be seeing you guys in a few weeks.
Thanks, Curtis.
Oh, and really briefly, I'll put the bulletin board post out there again, that this is where we'll post the solutions to tonight's problems and the problems for the upcoming Monday night calculus.
Right.
So, all right. With that, I guess we'll sign off. So hope you guys have a great evening, and we'll see you in a couple weeks.
Yeah. Bye-bye, everyone.
Bye.
Thanks.